Welcome. Thank you for coming today. We're talking about system error. It showed up in C++ 2011. It's in our standard libraries, increasingly so. And a lot of people are not using it, but you're going to see more of it. So today we're going to talk about that. The takeaway is really easy. Use enumerations. You don't have to, but you should. Use enumerations. And if you do, you're good. If you're users, you're done. You can leave. The talk's over. Library authors are going to implement with the design that's presented, and we're going to talk about the rationalization of that design. Is there a little feedback? Everybody okay? Okay, so here's the talk. Here's what we're going to cover. Introduction, what is message? There's a lot of conflating of error codes and messages. We'll briefly go through that. We'll talk about system error that showed up in C++ 2011. It's being used increasingly so with the new libraries dropping, like in 2017 file system and networking TS. And then some recommendations on its review. But there's diminishing returns. The important stuff's up front. So if we don't get through all of it, because there's a lot to talk about, that's fine. So the disclaimer is these are error messages. So there is a meme alert. I put little pictures in the upper corner so you wouldn't be bored, because error messages are annoying. Nobody likes them. So this is so you won't be bored. You look at the bunny or something while we're talking about the boring stuff. Okay, so what we're not going to talk about, what system error does not address. They're holy wars, hacker wars. There are message wars. Most of our systems, especially as the code bases evolve, there's 1, 2, 3, 4 messaging subsystems in there. Routing, this happened. I want to do conditional branch processing on this scenario that occurred. I somehow forward that back up through my API so that the caller can deal with it. The caller may be echoing to the disk, maybe popping a box to the user, maybe writing to a file, maybe sending something to another process, maybe shutting down the core of the reactor. There's conditional processing that may occur based on that. So these messages are event notification mechanisms that we use to forward back to the user. It's a way for the implementer to communicate with the caller. And there's a lot of contention on how you do that. The contention is largely based on how do you phrase algorithms, compose larger systems, and do this branch conditional processing. The error code is just an enum. That's how you should visualize it. It's a really powerful enum. It's a little bit better than enum. So this is some of the stuff that you would ideally deal with in composing and phrasing higher order algorithms. Conditional branch processing based on a scenario, an event, a circumstance, something happened. And different code bases, different environments, you have different house rules for how people want to address these things. Generally, we're not going to talk about this today. We're just talking about a super enum, which is error code, and clarity constraints, correctness. There's a lot of personal taste in how you're going to use these things. So there's minimal infrastructure for API implication. You're going to have an error code and you're going to pass it around. That's it. So wars. We have a lot of wars. There's misunderstanding and conflating messages. This is a really overloaded term. It's like static is a really overloaded thought. Messages, on the misunderstanding, we're going to conflate stuff. I'm going to give you the result of a scenario, a message code, an error code, and you're going to make a decision and do conditional stuff as a result. And conflating the branch processing and what that error code represents is kind of an issue. So how we compose and how we handle, that's generally the applicable thing. And the house rules are going to decide how to phrase up larger and larger scale. So kind of moving on. Messages, errors, exceptions. We have several ways of communicating with the caller about propagating up the results of a scenario. So the message, it is going to provide visibility, right? There was a state change in the system, better tell somebody. And something happened, better tell somebody. There is this failure scenario idea. A lot of time, error code, you're thinking there was a failure scenario, and I got to do something in particular to deal with that failure. Well, that's a negative test. Sometimes, a lot of times, most of the time, negative information, a negative result is actionable. So we're going to propagate and inform the caller, hey, sorry, this was good, that was not good. You may want to do some extra stuff. And then there is this exception idea, and this is you're not returning from functions. You're not making forward progress. This is a stack unwind, right? You're going backwards. You're unwinding, you're destructing, and you're going to hopefully catch it at some point and reset. So these are going to be the ways we're going to start handling errors versus exceptions. And kind of key to our mind, because error code is about composing and phrasing higher order algorithms based on actionable information from the communication of the implementer I know what's going on, and I'm telling you, the caller, here's what happened. How can foo finish? Finish the results of foo. Foo did something and it finishes. So, well, it can complete. That would be good. Foo executed and there was a return. Maybe return was void. Maybe it was some object. Who knows? But success or failure presumes the function actually completed. Well, it doesn't have to complete. You can throw an exception, right? That's a stack on one. You're going to go backwards. Or you can just terminate, so terminate or exit or something. You just abort. Well, now we've got this suspend thing coming along, right? We're going to start playing with coroutines and resumable things because it's going to be an interesting way to also start composing higher order algorithms. And of course, we still have to communicate back to the caller. Things are good, things were not good. Here's your information from which you can do your conditional branch logic. So we are a very rich environment, more so than most languages, because of our ability to compose. Error code is just a super enum, that's it. So operation completes, success or failure. Suspends, we've got that. And then it does not complete. This is a summary of what we just saw before. And all of those are legitimate ways for a function to finish and for us to communicate back to the caller in error code or some sort of information about we're good, we're not good, this happened, go ahead and conditionally branch. So error message, it's an error code. A lot of times there's an associated message with that. The caller is going to do something based on that. And this is one of the things you can do if you don't want to use error code. This is done a lot. It's surprisingly useful. We're going to call a function, it's going to return a string. Well, what's in the string? I don't know, there's stuff in the string. You want to know what happened? You parse the string. Maybe if there's like the word error, maybe it was an error. And that's a very open-ended design. So a lot of the higher order languages will do that. APIs that are unplanned will do that. It allows me to not establish enumerated results up front. I can just kind of wing it as I go and add stuff. It's not particularly well documented, but if you follow conventions like the word error means something bad and somebody does a regex on the screen and see the word error and they know that's an error, this actually works pretty well. This is surprisingly useful, even though there's no type safety here at all. And it's hard to document, it's hard to maintain, but it's surprisingly useful how big systems are built based on just returning a string. No enumerated state, no enumerated branch condition processing, but you pick up a lib, you see some strings, you start handling it, it tends to work, it tends to scale at some level. So those are examples that you could use if you don't want to use error code, that's fine. So we'll go down. Messaging and logging. Logging is a big issue, and error code does not help you with that at all. There are frameworks, there are many frameworks, there's syslog, there's a lot of in-house developed stuff, and most systems of size, most code bases of size, there's several of these in there. Several messaging and logging systems. It just tends to work that way because of the constraints of the latency of the notification or the path by which you route information back to the interested party. So I know a lot of people don't like error codes and messages because they're frustrating and annoying, and well, we all kind of admit we need logging though, because we have to suffer the systems that aren't behaving properly and figure out what happened, what's going on. So this is kind of the scale we're working at. So logging is necessary. You can kind of visualize that, big ball there. Logging is helpful. Logging is disallowed. And there are very few systems where logging is disallowed. They exist. They mostly existed, 10, 20 years ago, because now even your vacuum cleaner has a full TCP/IP stack in it. You can talk to it. But there are a few systems where you can't do logging at all, but the scale, we've seen this scale before. The scale is this. There's the sun, logging is helpful as earth, and the $100,000 tool bag dropped by an astronaut back in 2008. That's the very end case where logging is really not allowed or not possible or not going to solve what you need on the system. So definition of terms, we'll go through this really quickly because this is intuitive. You already know this stuff. So there are message frameworks. There are tracing frameworks. There's a lot of overloading of the use of terms in this messaging space. So, you've got that messaging across object boundaries, like, the old Smalltalk thing, and you've got messaging across CPUs. I mean, we have so many ways to talk about messaging, and system error is just an enumeration. It's just a way for the implementer to say, look, I have these scenarios, and I've communicated discreetly the scenario to the user. So the user can do conditional processing, conditional handling based on this very specific scenario that I encountered when running your request. So this is just kind of arm-wavy stuff, and that has nothing to do with system error. So here's more system error. Messaging framework and whether or not you're using syslog, whether or not you pop up dialog boxes, has nothing to do with system error. we're going to merely talk about a super enum that we can pass around through our code. That's about it. And it's up to somebody else to decide whether or not to pull in your own framework. So you can do branch logic on it. You can do very discrete handling of specific scenarios. You can have information payloads in there, but generally you'll have to add that on top. But the framework itself is something you bring external system error. Okay, it is a mechanism. What is it? System error. It's a little header, really little header. There's a class in there called system error. So, okay, well, the system error class you will see. And that mechanism will have an enum payload that you're going to receive and test against. That's it. If you're a library implementer, you're going to define the discrete set. You'll populate this error thing that you give back to the users. So it's a single event message definition or instance. And go down. That's terms for today, event. I'm just going to kind of skip through this. Essentially, bring your own framework. System error isn't that. It's an enum. That's it. It is nothing else. There's going to be a lot of stuff in the slides, especially at the end, that you can take the slides and play with them and review them. But the diminishing returns is up front. It's an enum. Think of it as an enum. We're passing around and populating enums. Library developers, there's some tricks on implementing the super enum. But users don't have to know anything more than using an enum. This is why system error did not even try to take on the framework thing. It's hard to build a message framework. So, in this case, we've got a lot of quadrants. Generally, we're talking about what is the volume of information produced and what are my requirements on being able to handle that at what latency. So the speed and volume kind of thing. And there's kind of a scattered need across the universe of where you might be in handling certain types of messages. In a lot of cases, of course, you don't have the same requirements for all error paths. Some stuff is the hot path, and you have specific requirements. Some stuff is in user time. You don't care. You've got all the time in the world. So you might end up with multiple frameworks, and we do. Most of our systems have multiple frameworks because that's a hard problem. System error does not help you with that at all. It's an enum. So this is an example of contrasting in one product, a network appliance perhaps, the data plane from the control plane. There are different requirements for latency and volume of information, and the framework has to deal with this. System error does not do this. You bring that yourself. System error is an enum. So we'll get in specifically to what it is. But this is what we have, a lot of people are familiar with now. But let's just go through an example. What if? What if I want to say, well, there's this concept of a message that I want to do, a message definition. So somewhere out there, you can put it maybe in a header and call it SIGSEV. And maybe you can put some kind of definition in an implementation file somewhere else. And you want to define what a segmentation fault message would look like. It might look something like this. Now, this is a little bit hard to read. That's not the point. The point is somebody defined that message ahead of time. They said, look, this is a scenario that may occur. I'm defining that. And this happens to be some code that you may see. There is the point at which the notification occurs. The event happened. So up above, we just defined it. Hey, this may occur. It's a scenario I handle in my code. But the event notification is the idea that I actually encountered that scenario. I encountered that condition. This message could be created and handed back to someone to handle. In this particular case, the message echoed this system out, or standard out, or standard error, or wherever it came in from the console. And you'll notice that the string down below, segmentation fault, is suspiciously similar to that string up above that was defined in that implementation file. So somebody had defined these things. Some had a priori knowledge of this scenario. This condition is something that may occur. So we can do various tooling to maybe decorate this thing up. So in a lot of cases, in this case, we're running with, what is it, Valgrind? Okay, so you might have instance-specific timestamps or key value pairs if you're doing structured logging, or instance-specific additional context, additional state that kind of carries along with that message that might be useful to the caller, to the user eventually. So that's ultimately what's going on there. System error basically is about defining a super enum, and this additional context may carry with it in a real-world event notification scenario to help with conditional context and branch processing and logic for the caller. But this is the contrast between I defined a message that may someday occur, the message actually occurred. System error, that's what it does. It does this. Okay, so for today, Event notification, it's kind of like system error is an event. Hey, look, there you go. Maybe it was good, maybe it was bad. It has no judgment on you or the implementer. System error is just this neutral payload saying back this scenario occurred. So your framework, go bring that yourself. But the idea of event notification, the idea of giving you an instance that you may choose to log or carry forward or pass on to some other process, system error is kind of built so that you can carry it through your APIs. Okay, so error codes and messages. What are they? Okay, a message, that's segmentation fault. It's typically human readable, doesn't have to be, it could be a machine interface. And it's going to be some kind of a descriptive string, maybe there's instance specific state tied to it, that's sort of a carrier saying this occurred, tied to this enumerated value, this enumerated discrete scenario that we had a prior knowledge of establishing, and then we forwarded back to the user, and they were expecting it because they read a documentation saying, this function may cause these enum errors to be returned to you. And then you would say, oh, now I need to handle them. So system error, that's it. That's what it does. So a message is a notification of a condition or a state change. That's typically why we're messaging. And what's a little interesting is message identifiers. This is kind of one of those holy war things. And some of the tools are really good about, they'll have a unique identifier for every possible message. And some won't do that. And if you have a unique identifier, well, that's good because you can type it into a web search and find out what's going on. If you don't have that, the whole message implicitly becomes the identifier. And it's surprisingly useful that you can do it like that. You can have a message identifier, which is the whole message string. Here's a message string. So I want the output to be that error comma value must be between 1 and 20. That's what I want the message to be. Well, there are a lot of ways that I can type code to get that. Now the first approximation, I'll just hard code everything, and then boom, that's my message. How hard is that? Well, I don't have to do that because if I have like a min-max bound thing, sometimes you don't want to hard code that. You would like that to be more conditional or situational. So I'd like a more reusable message. I'm going to lift out some local context for min-max, and I'm going to serialize out this. So we're going to assemble the string on the fly. Well, okay, printf will do that. So I can now pull the string out fully, and instead of having the stream serialization, which when you have big messages, the stream serialization gets really unwieldy, which is why Python went to the next one. Oh, well, actually one after that. From printf to fprintf, we're changing our target. This is where the user is making a decision on destination. Now the other ones, the decision was sort of implied on destination. Now the user's deciding, or the implementer, the guy writing this algorithm, is deciding the destination. So we're talking about what kind of power are we giving the implementer in employing this message. And then this is kind of the Python-y thing, where they're lifting out these formatting strings, and then we'll have the context like min-max or other conditional information that we might want to drop in there. And then you can build higher order things with structured logging and other stuff. So this is all giving us ultimately that same output string. Here's another one. Now this is interesting, these last couple. So the other message is we were sort of implying these are just strings going out. And now we're starting to establish categories or classes of errors, right? There's a whole family of errors, there's a whole family of warnings, a whole family of informational things, or maybe debug things, or verbose things, or trace things. You can have as many categories as you want. We're starting to apply categorical information to this string. So that's interesting because now we're giving the author of this code the ability to say, well, look, you can define min and max, and you can define the format string, and maybe you can define the destination, or maybe you can define the category, and I'll pick the destination in the library or in the framework. System error is not the framework, but these are the attributes that we want to start applying to this thing where, whoa, that happened. What happened? Config didn't load. What happened? The user file name was bogus. It wasn't on disk. It was the wrong format. There's a scenario, and we're starting to add context external to what that thing means. And the context is not the same across the code base. Sometimes it is, but sometimes it's not. So, and then here's another one. Now, this last one is interesting because what we've done is we've removed from the programmer the ability to make bad spelling mistakes. Now, there is this enumeration now in this, like this error val out of range thing. So I'll let you in your context to establish min-max bounds. I'll let you pick the enum, but you don't define the enum, you're just picking the enum. And you know what? You can't insert profane words in error messages. Have you ever grepped your code for profane words that might show up in front of the user? Apparently there are code bases that'll do that. There are stories, many. So this bottom one, that looks a lot like what system error is going to do. It's going to be like this. Okay, so we want to empower the developer. Well, a lot of times we don't want to empower the developer. The developer doesn't want to form well-phrased, well-spelled expressions of text that go in front of the user's eyes. Sometimes yes, but we don't have to. So in these top examples here, we are giving you the first one, infinite power. Type whatever you want, go nuts. And you know, hopefully there's a review, you know, by other developers. But the top one, you have infinite power. And as we go down, we're going to start changing the power you have to pick your destination or pick your error category or kind of your other stuff. But this is kind of some of the things you're allowed to do. You know, you can pick your level. Yeah, well, for you, opening that file was a warning. Look, I was looking for defaults, I didn't find it. For me, it's an error. If I don't have a configuration, I can't boot the hardware. So it's possible the attribute of the category, the classification of errors, that's tied to the circumstance, or it's tied to the message. Could be either one. A lot of times you'll go one way in one area and one way in the other. So those are overrides. These are kind of some of the examples. And the key point on the bottom one is look at what the developer is allowed to do. The developer is not allowed to misspell words, is not allowed to define a badly phrased, confusing, ambiguous statement. Somebody had to do that, but the person handling this scenario in the code is not. All they're allowed to do, in this case, is establish min-max and pick an enum. And if you pick the wrong one, well, you know, ideally there would be a check for that, but you actually have to pick an enum or it won't compile, right? We're picking up an enumerated value from somewhere. It'll either compile or not. So this is a maintenance point, and we've given the developer minimal ability to override with this kind of thing. And whether or not you want to break out the classification, the category of error or not, that would be a personal choice. System error doesn't care. System error is going to give you the bottom one. Okay, so invoking a message. Something happened, I want to tell someone. Okay, identify and provide field values. Now, system error as it stands is not really good at giving you payload instance specific state. This happened, I couldn't open the file. Well, what file? Well, I don't know. That's not system error's job in its current incarnation. So people typically put a hash or key value set or something like on that. And there's a whole world of structured logging to deal with state and stuff. There's some libraries like the Boost Outcome library that are specifically addressing stuff like that. But we are identifying messages and we're invoking them. It'd be nice to be able to override destinations or override warning or error level or, you know, maybe kind of make other fiddly changes, but it's sometimes dangerous to do all that local overriding. So these are going to be house rules in your messaging framework to decide how much power you want to give the developer, but by default out of the gate, and he knew. You should use them. You don't have to, but you should. System error doesn't require it. Life is easier if you use enums. Okay, so making it easy. You're not going to get better than this. This is the least code you will ever type. Name a way for a developer to say, this happened, you deal with it, not my problem. You know, I'm just telling you, couldn't open the file, or disk is full, or whatever it is. Saying my log with an enum is the best you're going to do. There's nothing else. Now maybe it's going to be my log with an enum and some local context, like min-max values or some other information. That's the best you're going to do. There's no way to reduce this further through implementable code. But that presumes, that assumes, that expects, that demands somebody somewhere out there made an enumeration. Say, these are the discrete states that may occur, and then you can use them. And you probably, you don't have to, but you probably want some sort of text, some sort of user viewable review of what does that enum mean? What is the thing, what is the message that actually goes to the log file or goes to the user's eyeballs? Well, so this enum and this table of strings, it's going to have to be defined somewhere. And system error, that's what it does. It's just a design. You could come up with other designs. This is a simple one, and it's using a little bit of type traits, but it just presumes, you know, enums are really powerful because when you have an enum, especially with C++11, we have strong enums. You don't need strong enums, but strong enums are an example of how from enum I know the type, and from the type I have all these traits tied to the type. And now with the magic of metaprogramming, you can go nuts. You can associate all kinds of things with other things, and system error is basically doing it. What is it? Well, it's not your logging framework. You go and bring that yourself. System error, it's two things. It is an adapter. You can take whatever super weird, stupid thing you have, and you can shove it into a system error object, and then pass that thing around by value, safe slicing. So by value passed around system error, it's an adapter. It'll unify across your error subsystems. That's what it does. It's also a design, an implementation mechanism where this thing called standard error category, and you're going to derive from it to put your enums in there. It's a decision made by the committee on how this will occur, how the implementation will occur. You'll hook into the framework, set your enums, and you're good to go. But in theory, all your APIs can be passing around stood error code, and all your errors are propagated across third-party binaries. You start loading other systems, they're giving you error codes. You're a system, you're giving other people error codes, and it's a common interchange mechanism. That's what it is. And that's why the file system TS, the networking TS, and some of the other libraries coming in from C++11, that's why it's doing stood error code. Prior to this, we didn't really have a way to pass errors around in a standard way. That's what this is doing. Okay, so what's in the box? It's not a big box, it's a little box. Open up the system error header. It's not a big header. Okay, well, if you're a user, you kind of don't need to know any of this stuff. It doesn't matter. What are you doing? I see enums, I test against enums, I'm a user, I know nothing. Cool, that's it. You should not have to know anything. If you're a library developer, if you're authoring or creating these things, this is the stuff you kind of have to know. And of it, you really only care about a couple things. There's this thing called error code. Use it. You're going to receive it, so you'll have to be able to decompose it or compare it with something. You'll compare it with an enum. You're done. Error category, that's for the library authors, the implementers that are trying to establish the finite bounded set of a priori scenarios that may occur that you want to communicate back to the caller. These are the enums I may give you. And maybe there's some documentation associated with them. Users will be happy because, you're saying there are 5 ways you're going to tell me you were upset. Yes, there are 5 ways. Here are the 5 ways. Handle the 5 ways. We're all good. Error categories for library authors to implement this. So we'll go into that very briefly because there's not a lot to know. And then there's some other junk in there. And you don't care. It's just going to work. It's basically going to be obvious. You don't have to know those details. And there is a confusing thing that's going on in the community of, is it an error code or is it an error condition? And for the most part, you don't need to get involved in that confusion. Error codes are in your APIs. Error codes are received from other APIs. You'll be using error codes. The library author may have to make some decisions whether it's code or condition. Well, you have this now. It came in C++11. It's standard in C++11. So if you're on a 98 or an 03 compiler, you didn't have this. Oh, but wait, you do. Error code, it predates C++11. It's found in Boost. It's ready to go, ready to rock. If you're 98 or 03, just pull it in from Boost. Oh, you know what? Osseo's got fully implemented. This is the basis of the networking TS. So the system error stuff kind of came out of the Osseo networking TS stuff. So there's a full implementation there too. Pull the Boost implementation, it's fully ready to go. Pull the Osseo implementation, it's fully ready to go if you're on 98 or 03. But if you're on 11 and beyond, you already have it. So everybody in the room, we all have this stuff. We all have it right now, depending on which library you want to pull to get it. Okay, so this is all we really care about. I have an enum with my finite, discrete, a priori established scenarios that I may want to communicate with the caller. This happened. And I probably have some kind of string or descriptive association to that enum. Somehow, magically, this has to get tied to the invocation. So my log, and then I put an enum in there. My log, and I put an enum, maybe some additional context in there. And the top, you're going to use error category to implement the top, and the bottom, users are going to receive error codes. You, as an implementer, you're going to be populating an error code to go back, and it's not hard. Error code equals this enum. You're done. It's like not hard. Okay, how does it work? Well, I want to write this code on top because you're not going to get better than that. You're not going to have less typing than that. You're not going to get better type safety than that. I somehow want that associated with the implementation on the bottom, which is going to be defined in an error category. System error does that. So this is a pattern. It's a pattern we see a lot. It is, whoops, up. You can call it something else. I'm calling it the handle and context pattern. This pattern is so used that I'm going to take a moment to beat a dead horse and say how much it is used already in your code. And system error is using the same pattern you're already using in your code. So it's magic. So as an example, this is the same pattern. And don't answer yet the question, what is T0? Let's look real quick at okay, there's a worker and another worker. And, okay, int main void. Okay, I am a thread. I'm the main thread. I'm going. I am a thread. Oh, you know what? I want to make another thread. Let's call it T0. No, I want another thread. Let's call it T1. I want a million threads. Go make a million threads. Go nuts. Well, what is T0 really? What is T10? It's not a thread. And you know what? I gave you a hint. Next one. Hint. It's not a thread. How do we know it's not a thread? Before you answer that, it's always good to say, well, how big is it? And well, you can just do a size of it. And well, it's little. It's not big at all. But well, wait a minute. I know threads, they like have a name and a control block and thread local storage and thread statics. And there's a lot of stuff in a thread. How can T0 be like so little, like size of a pointer or something? And that's because it's not a thread. What is it? It's a handle. It's a handle to an implementation defined thread. There is a thread somewhere. Somebody implemented it. It's a handle. It's a handle. And so we have this light and fluffy, lightweight thing called a T0, which is not very big. And it is a handle to an implementation specific. And this is the power of C++, right? We can stick our implementation defined thing over in that lib that we're not even going to load till runtime. And all our code still works. We don't even have to recompile. That's kind of cool. So what pattern is this? And that's the pattern. This is the handle and context pattern. And so we're gonna go through a couple examples, but this is really the key question. Where's the context? Okay, so I have a handle. Where's the context? So next slide. Okay, well, if this is the handle and context, if T0 is a handle to an implementation defined thread that's somewhere else, where's the context? You want to take a shot. It exists. It better exist or we're screwed. In this case, the context is the entire process. This is the wimpy way to go. You cheated. You always have the current process. You can always go to the current process level, globals, and state and start interrogating and doing stuff. The thread is assuming there is a context around it, and somewhere in that context, somebody is saying, I want to create threads, but as these things are created, they're uniquely coordinated amongst each other, so there's no thread 1, thread 2, thread 3. Oh, I have 4 thread 3s. No, there's only 1 thread 3. Somebody is brokering and handling the unique naming of all these threads. The context is doing a really important job handling resource allocation of oversubscription, or the hardware is already taken by somebody, or the context does a very important thing, but that's invisible to us. We're just creating handles, and magically the context popped into existence. And so the context exists. It may be a singleton, may be process specific. There may be more than one context. In the case of threads, there's only one current process. So there's only one global context for threads. A handle is constructed within a context. You may have more than one context for some designs, but the handle only makes sense within the context for which that handle exists. And you can have dead handles maybe with no context, but the handle's meaningless outside its parent context. The system maintains design invariance through the context. The context is doing the heavy lifting. The handle is not doing the heavy lifting. So design invariance, we have a lot of them, and this is the power of our systems, but other things like, read-write coordination or allocating of scarce resources or, other stuff, there's stuff that you would want to ultimately handle always through the context and never through the handles, because those are just lightweight little things. Okay, so here's Alexandrescu's allocators. They gave a talk at a couple of years ago. Funny story in the upper right-hand corner. They did successfully surgically reattach his hand, so that was, good. My allocator equals, so Alexandrescu proposed these composable allocators where you could establish policies for strategies for how you want to allocate blocks and how it would handle that. But you created an allocator and then you would allocate little things from it, you'd play with them, and then when you're done with them, you would give them back and they would, be cleared up, they'd be freed. Well, this is the handle in context, right? So I've got a handle to a memory thing that I allocated. And then when I'm done with it, when I want to retire it, when I want to get rid of it, I return it back to the context and it'll coalesce or not, or however you establish your composable allocation strategy. This is a good example because this is an example where the context is in your face. You are managing the context, you are managing the handles, and there is this association that a handle outside the context makes no sense. So in this case, you're charged with holding those associations together. Okay, so why do we do this pattern? It's done a lot. We do this pattern because it is really, really fast. That's ultimately it. I want to do centralized control of design invariance for something, threads or hardware or memory. We always are dealing with scarce resources. So I would like to reuse things. I would like to coordinate things. I would like to control things, but I want to make it easy. So we do value semantic handles being passed around, but the context is established in this sort of hidden place. And so these are kind of example domains, network, file, thread. There are a lot of places where this pattern is really, really popular. And almost always it tends to be amortization of a scarce resource. That's always a good way to drop to this pattern. And, error messages, anytime you do string manipulation, that's expensive. That's very expensive. It'll impact your latencies. Amortization of scarce resources tends to be interesting. Okay, so shared pointer is actually the handle in context pattern, whatever you want to call it. So we have this owning pointer called shared, and we have this non-owning pointer called weak, and they're both referencing objects, and somehow they're both sharing the same, the control block, the link count, the object itself that they're referring to. All that context, these handles are sharing. And magically it just works. Well, yeah, because the whole point of this context pattern is the context will establish invariants that are controlled. And handles are just lightweight ways to reference through the controller. So this handle of context, we've got owning and non-owning, and we can kind of see the control block exists, we're aware of it, but many, many contexts exist because many objects may be. This is so popular, so powerful, you can really drive a semi-tractor trailer through it. You can do a lot of mischief with this pattern. But we're already familiar with it. We're beating a dead horse. It's light and fast. It's controllable. This is. I'll leave the slides, but I want to get to the code because that's more interesting. Just library developers are going to have to be aware of a couple of things. Users know nothing. They receive a std error code. They test against an enum. Okay, the message category. This is what a library developer cares about. Users do not care. Users do not care. Users do not care. An aggregation of messages. Hey, there's this domain of all these enumerated values. This is my category, my domain. I think domain would have been a better word. It's error category. You'll derive from std error category, and you'll put your enums in there, and your associated strings will be with there, and that's it. That's all we're going to do. This is not hard. This is like 15 minutes of work. So you might have a lot of domains. Well, these you get out of the box. C++11, there's more dropping since C++17 came a few days ago, but these are the common ones. Now look here. Namespace std, we've got this errc thing. That's your POSIX errors, right? These are commonly understood scenarios that may occur. And they're there, they're ready to go. You can catch an error code and test it against any one of those. And if it equates to that, if it's equivalent to that, that's what happened. So you can just use this now. You don't have to define your own. These are ready to go. But some domains, they want to define their own errors. And that's what error code does. Have as many domains as you want, go nuts. You'll probably end up defining your own domains for your own domain-specific issues, and you're just going to make an enum, slap it in a namespace. But these are right there out of the box. Okay, so I'm going to skip through because you're not actually going to write code like this, but there is a global process singleton, kind of like you have one dealing with your thread allocation and coordination. There's a global process kind of thing that is establishing your singleton for your category. So these are singletons that exist in the standard. You link, you run, these are there right now. Each of those categories have names. It's a process singleton. It has a name. It represents a category or domain of stuff that may be interesting as enumerated concept. Okay, error number. We're dealing with this a lot, and this is kind of the old way we used to do it in C. You don't have to do an enum, but it's a good idea to do an enum because you get type safety. But a lot of code is C, and C is doing this error number thing, and that's kind of like the thread local global that gets set when something goes wrong. So it's set to 0 at process setup, and people can overwrite that value. So when you call a function and something bad happened, like here, open the file and you get the file descriptor back, and if the file descriptor is less than 0, well something bad happened. Well, what happened? Well, I don't know. Well, let's go check the global called error number, and we'll test it. Now there's even this little formatty thing, stood stir error, and it's not thread safe, but it'll give you a little descriptive string saying what happened. So that global is set associated with a lot of system kind of calls where there's no error path, there's no error code being returned to you. So you go to the global yourself. So it's kind of a hidden context that keeps getting overwritten as your thread makes progress. So if you want to know what the error was, you better hit it quick because it'll be overwritten by the next error. So get last error is a similar thing that Windows is using. Error code is generally a better design for this. The APIs are going to be more thread safe, but also depending on your view of the world, Linus Torvalds doesn't like the error number. He thinks it's flawed design. That's interesting, but error code is a better way to do the same thing. Okay, here's Ozio. Ozio says, look, I'm writing this networking kind of stuff, and I got my own class of problems here. Everybody's got their own class of problems. So Ozio chose to break out 4 different categories of errors. There they are. And it's not hard. You just find your little enum, and then you're going to get your category associated with the enum, and that's it. When you write one, you're going to do the same thing. Define your enum and get your category associated with the enum. This is the #1 most confusing thing about system error. And I urge you to not be confused by saying, use error code, don't use error condition. You can't go wrong. If you want to use error condition, you can, and then you can explain to people why you did it, but it takes more time to explain than to actually do it. We'll explain why they're different. And this is part of the design. It's interesting, but our APIs will pass stood error code. Our APIs will not pass stood error condition. Even if you want to use stood error condition, your APIs will not pass stood error condition. They will pass stood error code, error code, error code. Platform-specific behavior is inconsistent across platforms, by definition. This contrast between that which is specific to this platform or which is applicable in a consistent way across platforms, that is the difference between error code and error condition. Now, developers may get confused, but we all respect that this is a scenario we sometimes have to deal with. Some of our stuff is platform specific. So I'll just skip over this, but message IDs, message code, message values, well, you review the slides later. This isn't helpful. I really need to get to the contrast between code and condition. The reason they came into existence, and this is C++, this is not other languages. Other languages understand this thing called error code. The idea of it, we have one in the library called error code, stood error code. But what does not work, the reason we have this design is, if you say there's this one class of errors that we all trust, we all believe, a committee made them, so they must be smart, so we'll all just use them. We'll map our context into the standard ones, and everybody will just use the standard ones. That does not work. That presumes there's a standard one, but in reality, there's always domain specific. It's supposed to work by having a common denominator that we all accept. The reality is that common denominator doesn't exist. That's intractable, it's non-scalable. So we have a design where we allow mapping of my domain to your domain, comparison, equivalence of my domain to your domain. That's what error code's doing. So a universal enum that everybody uses, that's not what the POSIX errors are. Those are just common scenarios that sometimes happen, but that's not the universal set. There is no universal enum. That's the design of stood error. Mapping across enums, easy. That's what it does. So the standard one, the implied mechanics is everybody maps the standard one, and all our error scenarios, all our conditional branching is based on standard errors. Does not work. That's why this design's there. You can review the slides later, but it's lossy, introduces ambiguities, and it cannot scale because there is no common domain. It does not work. What we do is, you have a domain, I have a domain, lots of domains, mapping across domains, that's easy. And that's what error code does. So we're going to map domain specific to standard, and this is kind of the same thing. This is more detail with what we just said, but I have to zip on because I want to see code. Domain specific errors must exist. They always must exist. All of our code is domain specific. It turns out there are a lot of domains. Who knew? Translating is lossy. That's hard. The design of error code is to say, I do not want to do a lossy operation until at the point of use. That's this design. And that's why all your APIs will pass error codes. Error codes are a non-lossy platform specific. This happened with your network controller. And then you propagate it up. And if you want to do a lossy conversion at the point of test to go to the log file, that's fine. That's up to you. That's the point of use. So many message codes from many domains, mapping them across different domains. Even across third-party libraries that you have no knowledge of at system load. That's totally fine. Error code is built to do that. We want to preserve context, and we want to map and manipulate across domains. Now, this is surprisingly hard. How many domains exist, and how do I want to translate all the weird things that may happen with that particular hardware device up to something that my generic library can present to the user in an understandable way? That mapping is work. That's design work. That's not system error's fault that the design work has to occur. So we're going to call that cross-domain semantic mapping. Cross-domain semantic mapping is hard, and that's the heavy lifting. This is done ultimately through static type checking of instance-specific. You'll pass these through your APIs, code and condition. Always error code, never error condition through APIs, and we'll test against any enum. And if the enum's a code or condition, you won't know, won't care. Okay, so what is, it's a little thing. It's 16 bytes. It's suspiciously similar to 8-bit or 8 bytes for a count and 8 bytes for a pointer. It kind of looks like that. There's sort of this associated state with an error instance. You get an error code, you test it against enums. That's all you're going to do. If you want the string, ask for the string out of it. It'll give it to you. The string is not actually in that little instance. It's in the error category. It's in the context. It's hidden from you. So the domain and ID is the error code. This is the API of error code. It looks a lot like the API for error condition. What can you do? Well, you can get the integer out of it, which is an enum, ultimately. You can get the string message out of it, and you can clear it. You can test it for, do you have state or not? That's the operator bool. And you can get its parent category. Probably don't care about that unless you're a library author. You may care about that. Users don't care about any of this. Users will test against an enum. That's it. That's all they'll do. But the library author, this is the state that you have, and ultimately, it's a lightweight handle into the error category, actually giving you the string state. So you're going to take the category, derive your own process level singleton. It doesn't actually have to be that, but out of the box, it's easiest to do that. And you're going to stick your enums and strings inside your category that's derived. So this is kind of the same thing. We already have a few categories given to us. You can have as many domains as you want. They're all going to derive from error category. So here's code. This is normal. I'll create an error code and I'll pass it into a function to be populated on the left. Or I'll just call a function which returns one by value on the right. Totally fine. Both those patterns are widespread uses. This would be typical. So error code, lightweight value semantics instance. It's handled something, but it's basically got an enum in there. You're going to test against some kind of enum. In this case, we're doing an implicit conversion. We're using that operator bool. So, hey EC, do you have something in you? Now it could be all kinds of stuff. Maybe you're saying, yeah, I totally started that asynchronous process just fine. That's not actually an error. It's just saying whether or not there's payload in there. Now, I find it's interesting to test against the bool, but a lot of times you'll actually want to test it discretely against an enum. That's going to be the next slide. So this is just a value semantic lightweight little thing. They're little. They're fast. This is why. This slide is all users have to know. If you forget everything else, blah, blah, blah stuff, this slide is the slide. This is all you need to know. You will create one. You will maybe get it populated through a function or populate it yourself, who knows. And then you're going to test against an enum. That's it. And as long as the library author did their job, that'll work. And it's not a hard job to do. We'll zip through that. But what's interesting here is not every error is an error. This is informed context back to the caller that something was populated because, yeah, I hit a decision point. I have information for you. I failed to create that directory. I am so sorry I failed to create the directory. Why? Because the directory was already there. Well, I just want the directory to be there. This is not really an error. I'm fine. I just want it to be there. So in this case here, we have an optimistic scenario where, as long as you created it, or the error was it was already there, okay, well then I can continue on. This is conditional branch logic based on communication from the caller. But all we're doing, that's it. EC double equals sum enum. Or you could have said EC is assigned the value of sum enum. And that's it. That's all we're going to do. So there are standard error category stuff all out of the box ready to go. They're in the standard. The error code's historical. I'm going to skip through this. The condition, this is a domain context thing. And the slides are free. They're going to be online. So, you can read them at your peril, but we're running out of time. We're going to map across through stuff, but ultimately what I'm trying to get to is the simple way to, this is me being cute. This says use enums, is all that slide said. Library author, this is not hard. You're going to make an enum by define the enum, write a switch, and some lightweight template metaprogramming, which you can copy paste. This is 15 minutes job. This is what the library author does. So most people are not library authors, they don't care. So the standard uses strong enums. Osio is using weak enums because they're trying to be, backwards compatible, low 3. Use whatever you want, but both those work. Your enum is a placeholder for error condition constants, and you're just going to test against it. If this error code that I receive from somebody is that scenario. And the library author is going to define the enum, overload some decision about I'm a code or a condition. Almost always, well, the guidelines here, it's a little arm wavy, but if you're doing platform-specific stuff with your hardware-specific controller, it's an error code. Otherwise, it's an error condition. When in doubt, just use error code. Derive from error category, and you got a couple overrides. So given your enum, what string would you like to return? That's it. That's not hard to do. It's often done in a switch. Given your enum, what string would you like to return? That string happens to be, it's passed by value. We're returning a whole value string back. So if you wanted to do a locale-specific translation, or if you wanted to pull other context from the environment, put timestamps in there, the API is conducive to that. You can access it. So this is library author step 4. We're going to get our singleton. And now you can just get it. It's just sort of an identity thing where the address of it exists in the same process. Define the factory functions. These are well known. And this is not hard. You just anything that can be converted to an int and a pointer to or a reference to a domain, that goes into error code. So C errors go in, information from other processes go in. As long as you convert it to an int and a reference to an error category, you've got an error code. So make one, make the other. There's some overriding of equivalence and getting of default stuff. This is what the library author can do. This is optional. You don't have to do this. But this is where the author can say, look, I got a lot of domain-specific enums, but you know what? A lot of these kind of map to the POSIX enums, the standard enums. So this is your opportunity to kind of map your enums to the POSIX enums. Now, you can test your failure scenarios with the POSIX ones, back and forth. That's if the library author wants to do that. This is cross-domain semantic mapping. This is a design activity. You have to define your enums, and you have to define their mapping, if there is any mapping to these other domains. That's the heavy lifting. That's the hard job. And this is just the easiest library that's standard to give you that. And that's it. So that's library author. 7 steps, one of which is profit. The one prior, 6 is optional. So it's really only a few steps. It's only 15 minutes to make one. Welcome user. So library author. Anything that can be converted to an int and a reference to a domain is an error code. Anything. So you can make error codes with an int and a reference to an error category. That's really, really simple. And there's a lot of mischief you can do with it. So users just need to know enums. That's it. I can read and see the enums that might be handed to me so that you can put them in your code and write an if. That's it. That's all users should know. They shouldn't know any of this stuff. They should use enums. And this is kind of how and why it works. This is the type traits template metaprogramming design feature that is error code. So I have an enum, and given an enum, I know what its type is. Its type is whatever enum type it is. Well, that type can have traits associated with it, and that's the mapping. That's why it works. Given an enum, I already know the category. The attribute for this enum is it belongs to that category there, that domain there. So that's why we just use enums in our code. So this is, if you're a template meta guy, that's really why it works. And this is, this day and age, really simple at metaprogramming. So users, this is it. You're gonna get one, populate it, you're gonna test an enum. That's it. That's all users should be doing. Nothing else. They can populate them. Users can just populate error codes too. If you have an enum, just throw it in the error code and hand it back to somebody or return it. So you can return them and populate by value, or you can throw. And there's our explicit conversion, but that's it. This is all the code we would write. And so now there's more stuff associated with it. You're going to want to test explicitly. You're not going to want to put them in a switch. And mapping across domains, this is the library developer thing. And I'm just going to kind of go through this very quickly. But the original context is preserved. Error code is a non-lossy platform-specific payload of what specifically occurred in a non-lossy way. That propagates across all the APIs you have into a third-party library and all the way down for somebody to handle. And if they want to test it at that point of use as an error condition or something, that's at point of use. That's number two. But mapping across domains is the library author's job. That's basically what we do. That's the design. It's a simple design. It's the handle and context design. And we're already using it. So library authors, they really have the hard job. What are your domains? Going to define enums for them that at least serves as documentation and do that mapping. Users, they use enums. They don't have to know anything. They shouldn't know anything. And you can define an error code in like 10 minutes. Users, 0 minutes. They just have enums. They just use them. So many domains are interesting. Domains overlap. Mapping across domains is this design. The error code is a type-erased platform-specific payload. The type erasure is because it's referencing an error category, which is an abstract base class. That's the type erasure that allows error code to work. So this is equivalences. Oh, I'll just say here real quick. There's more, and I'm not too worried about it because there's some really good blog posts by Chris Kohlhoff and others online that I'm going to point you to in a second. But this comparing of error code and condition is an equivalence comparison, and that's part of the design. That's the static type checking the compiler's doing. I can map any errors, any enums I want from any domain into an error code, and I can compare that against any other domain, and it'll just work. As long as the library author did that enum mapping, we're good to go. And so here would be an example of it. I have a lot of things that may actually have occurred, but I'm going to raise it to a higher order and say, there's this kind of domain where I just want to know, is it low system resources? And if any of those errors occurred, that equivalence to low system resources will return true. This is really powerful. This is a multi-state, many-to-many state reduction opportunity, and this is up to the library author to design that. So this is, overloading equivalence, and this is a platform-specific mapping. I'm not going to do it because you can do the slides online, and there are examples, blog posts on doing this, but you can do your cross-domain mapping in a platform-specific way. That's this slide. The link in the corner is Chris Kohlhoff's blog. It talks about this. And here's a platform-independent way to do a cross-domain mapping. So these are common ways to do platform-specific domain mapping and platform-independent domain mapping across error domain boundaries. So review, error category, error code, error condition. Users don't need to know any of these. They're going to receive error codes. Always APIs will use error codes. That's all users need to know. They'll test against enums. That's it. Library authors may care about, I derive from category, I populate error codes, but I provide users error condition enumerations. That's what a library author would care. If you want to throw one, no problem. That's system error. You just throw it. Throwing a std error code will give you the system error you can catch later. And the error CppCon stuff is ready to go out of the box. So for review users, all you're going to do is test against enums. It can't be const expr. I think that can be fixed. But as it stands now, it's not a const expr thing because of the way it's implemented with error category. For library authors, this is all you're going to do. You're just going to pick, am I a code or condition? Just pick code. It doesn't matter. Pick condition, who cares? And then derive your domain, access your domain. And that goes back to the academic thing of, are you platform specific or platform independent is that distinction. But this is it. This is like, 10 minutes. and then you got to know domain. And the cross-domain mapping is free, API type erases. So here's the blog post plus stuff by Chris. API design, and this is basically stuff you're going to know already, but the power of an enum is not just that it's an enum and it gives you compile time type safety, which is way cool. It's documentation. These are the discrete things. And now I've told users what the discrete things are as documentation, really valuable. But your APIs will use error code. They will not pass error condition. Always prefer error code. You can serialize to error code. You cannot serialize error condition. It gets upset if you try to serialize error condition. Just don't use error condition. Just use error code. Error code. Did you hear error code? So APIs should use error code. See rule number 1. Don't use error condition. Not hard. So APIs, error code. Oh wait, don't forget, your APIs should use error code, not error condition. This is an example of why you would want to use error condition. It's kind of academically interesting, but it's not practical. The code you're going to write, you're probably not going to return them. You're going to return by value. These are lightweight handles. They're little. So you're going to pass them to be populated or return them by value. You can throw if you want. And callbacks, same thing. Now, Osio tends to pass by reference, when they're read-only, and other people do them by value. There's a debate on that, and there's all kinds of opportunities for putting them inside std optionals and other things. So we're done, but using enums says that error code and condition. Error code, don't use error condition. Category defines a domain. The domain is your enums. And each module, each subsystem, many domains are probably going to be what you end up. You could have one big one if you want, but we tend to break out many. And system category, it's ready to go right now. All the POSIX stuff, just use them, pass them, return them, populate them, test against them. They work. We kind of know what they are. It's not the universal domain. It's a domain that is establishing common scenarios that we can all share. And this is kind of, the enums are doing our template metaprogramming type promotion to get the association of the magic cross-domain semantic mapping stuff. So that's it as a user. You're just using enums. Strong enums, weak enums, any enums. You don't have to use enums. Use enums. It's just easier. So converting enums to error code. And then, so I really am done. Don't write bad messages. Do write good messages. This is kind of like public service stuff. Content and consumable. This is what a message looks like. Where it came from, what occurred, how the system responded, what the user should do. That's what a message should look like. I mean, these are good messages, but we'll talk about that. So I'm done. So thank you to these people. There's a lot of offline kind of discussion on stuff. And what are your thoughts? Oh wait, should you use error code? Yes. Okay, and nobody needs to know anything beyond enums, really, except the library author who does 10 minutes of copy-paste. And then now you got a big enum that just keeps growing, and that's it. This is like brain dead, the easiest, best you're ever going to get for establishing common error interchange. So prior to this, we didn't have a way to interchange. Now we have stable ABIs, and BIs. So you don't even have to recompile. You can dynamically load in modules that have their own domains, not even recompile. It's just a runtime load, and everything works because the type erasure is through std error category. So you can write your own, and what they were writing prior to this was basically this. That's why they standardized it. So pretty straightforward. Anybody using it now? Error code? Yeah, it's in the file system networking TS. So, okay, there's a few. I know we're kind of tight on time. So anybody have any questions or comments? Yes.
Yeah. Quick one. It's actually a bit of a technical question. Halfway through, you were checking the Boolean state of error code.
Yes.
What semantic do you see from the Boolean state of error code?
Yeah, there's a debate on that. I'm in the camp where the Boolean state is not helpful. So a 0 value, a default constructed or one that was explicitly cleared, that'll have the value 0. So if Boolean test, it'll return false. I don't have any state. It's ambiguous as to whether or not I called a function who said everything was good, and they populated it with something that's not 0, but I started the asynchronous process. I successfully closed that handle, whatever it is. Because an error doesn't mean an error. It just means this scenario is information to the user. So I would recommend, you can do the if test EC if you want to then decide whether or not you want to discretely run them. But That's all it would tell you. It won't tell you whether it's good or bad. It just tells you whether or not there's payload in there. So I tend to not use the if Boolean test. But that's a point of debate. It is relatively new, and we're still kind of working on the paradigm for composition.
As usual, is this working? Testing? Well, as usual, it's an awesome talk, and I love the pictures. So there's only one fundamental question I have to ask. If what you're trying to do is present something to people so they understand what's going on, and if they can map onto the message that they get what's actually going on in the code, this is great. The problem is, that I see, is that you can have a fixed number of error codes. And in fact, a long time ago, I thought about this, because if you put all those error codes at the bottom of the system and say, here's my slowly growing set of enumerated error codes.
Yeah.
And then you go, wait a minute, I don't have the right one. I'm going to make another one. And you add another one. The system gets larger and larger and larger. And of course, these error codes are compiled into everything. And then one fine day you go, you know what? That's not quite the right message. It's almost right. You know what? I don't want to recompile the world. We'll use that one. And then things start to go south. And then eventually you say, you know what? I'm just going to say error, because I don't have a code for that, and I'm just going to use that. And that's when things have gone way too far. So the thing that I'm wrestling with is, I like all of this. I think it's great. It does what you want it to do. But the tension is, when you're dealing with a function, there are typically 2 or 3 or 4, maybe 5 ways that you can respond to the different kinds of things that can go wrong. It either worked or it didn't work. And if it didn't work, there are 5 different things. But naming them and saying, this is a read error, this is a write error, whatever, has to be filtered through every human's brain and come out the other side. And I will bet you that if we apply that test to everybody in this room, it will not be the same enum that comes out every time.
Right.
And that is my biggest concern. And to end that whole long preface is, at the other side of the point, when you have an individual function, somewhere in the documentation it has to say, here are the 4 flow of control points, and I am going to, as the author of the function, map this name, which is a pure mnemonic, onto this branch that the person will take.
Yes.
And my question is, how do you resolve what I just said, which was long-winded, with this wonderful presentation that does the other side essentially perfect?
Yeah, I think that's an excellent observation. And if I could kind of summarize your summary and see if it maps, there is a problem with error code curation. You know, the curating of ever-growing piles of stuff is like the curating of ever-growing piles of stuff in a museum. You have to manage them and redefine them and reclass them. And that's a maintenance point. It gets too big and it becomes unwieldy, and then people just pick what they think is closest. That's problematic. The error code design is encouraging you to create new domains when you have these new localized reason context things, and it handles the cross-domain semantic mapping. But your other point, which is an excellent point, is you called me and I'm telling you this is what I saw. And for me, my function, there's only 4 things, and it's one of these 4. And if you are very discreetly representing in the documentation of the function, here's how I communicate to the caller which of the 4 it is. You could have had a domain, an error category with those 4 things, but you didn't have to. You just do an int or something else. And that's discrete. That makes curation easier, because your curation is only for that function. But the interoperability, it is now not comparable to a POSIX error code or ASIO or other domain stuff. So if you have an error scenario that basically is saying disk is full and you've defined your own local disk is full, you didn't do the mapping to the standard version of disk is full. If that mapping was important, error code is useful. If it's not, that local reasoning, I think, is easier to maintain.
So the quick follow-up, to make this all work, all you have to do in your function level doc is say, here's my world, here are the 4 things that can happen, and I, as the author, have chosen the mnemonic, this, and this.
Right.
And if you get it wrong, it doesn't matter, because that thing maps onto this thing, and that's a fact.
Right. Yeah, and then the user, if they want to do the mapping, they can take that discrete, well-understood thing, and they can map it themselves. And yes, So I think that's an excellent observation, because what is not on here, and I know you guys want to go, but error code curation is its own world. And that's a big discipline, like all code maintenance is. So this doesn't solve that, just gives you an easy way to make a new domain that happens to be mappable to other domains.
So I just wanted to ask, how well does this handle many different error domains?
Yeah.
Because let's say I had, you know, an enum per function. If we take your example, you know, to its logical, ridiculous conclusion, and then provided, you know, mappings between all of these to like standard error codes,
right,
so that I can somehow have the users have helpful mnemonics and stuff like that, but I can reconfigure them later with stable ABI. How well does the system handle that? Like, is it built for that?
Yeah, there are two answers. The first one is it handles it great. If you have 1,000 domains, they're all type erased to error code, and they're all handled perfectly. They're all dynamically loaded, and they all interoperate just fine. So on the mechanical stable ABI level, you're good. What's not good is I'm writing a domain, and I don't know all the other domains that may exist. And the cheater's approach, which is a pretty good approach, and don't knock the cheater's approach, is I can basically map my stuff to the POSIX ones, because those are kind of understood. It's lossy, but once I do that mapping, I know everybody else knows what the POSIX ones are. So as long as the domain author does that mapping, you can kind of be blissfully ignorant of the other domains out there. And what'll tend to happen is some domains will organically grow. Osio is a networking TS kind of problem. They have networking domain kind of codes at a much richer level or different level than the POSIX ones. So mapping to the POSIX, well, if I'm actually writing another networky kind of thing, it could be I'm better off mapping sort of the Osio organically understood ones, and that's a gateway into other domain mapping. And the goal would be equivalence just works as long as every author maps to something that's relevant, like I'm mapping to networking, or I'm mapping to POSIX, or I'm mapping to, you know, my industry's pile of kind of commonly seen errors. That's the localized reasoning that the library author is supposed to be able to rely upon. You're not going to map to 1,000 domains. That's insane. You can't. It's not possible. But you should probably map organically to some common interchangey ones, which is all the POSIX one is. It's sort of a interchangey. It's not the standard one. It's a common interchangey one.
Okay, I have a follow-up. How big are these singletons that exist for each process?
Oh, it'll be compiler dependent, but it's going to be static data. If you want to do the minimum, it's all static data, and it's your string table and whatever the representation is for the enum, which is probably nothing.
All right. So how do you get a unique pointer out of every enum if you don't have any strings?
Oh, the error category is a singleton. The static linker will establish its placement in memory in some one and only one place.
Is this system amenable to error hierarchies? For example, suppose a company has a bunch of error codes that all projects in the company use. So
yes.
But then each project has some error codes of its own that have meaning only within that project?
Yes, that's a really good observation, and that's the trick of enums. So you can locally just say, I have a bunch of domains, and you establish the mapping. But in the hierarchy approach, the trick with the enum is this section of enums is kind of mapped to that other enum that's already defined, and you're kind of establishing an inheritance hierarchy of enumerated state. So because it's just enums, it lends well to enumish inheritance. Yes. Anything else? Thank you guys for coming.